All right, it's 8 a.m., everybody, at least in California. Thank you all for tuning in from everywhere across the world.
I
I'm
don't
excited. Sorry, what? Uh, David, did you run into it? Do you hear me?
I don't hear you, Jons. Is it only me?
Uh,
I don't either.
okay. Well, let me try. Okay, can you guys hear me now? No? Uh,
Yeah, not coming across yet.
okay. Okay, how about now? Can you guys hear me? Okay, wonderful. Uh, you prepare for these things, but technical difficulties seem to be the name of the game. Uh, all right, let's get the recording back on. All right, like I was saying, thank you all for joining us for LoFi 28. It's been exciting hosting these things over the last 2 years, how the time flies. Today's deck is also something that's really exciting for me because Dexy's been mentioned a couple of times by people. I call that organic sort of invite. So I had to chase David down to give us a talk, and all of the other speakers that are lined up for the day will not disappoint as well. So up first, like I was saying, David will be sharing to us about his journey building Dexy and Dexy Cloud. He's been helping people kind of wrangle IndexedDB and all the ways your browser store kind of gets screwed up for many years. And I'm really excited to have you on the call. And a brief word about our sponsors. Thank you so much, Jazz Zero and Electric SQL for sponsoring the Lo-Fi Discord website and our efforts. It wouldn't be possible without those people. So over to you, David.
Thank you. Thank you very much. I'm I'm a bit new to this forum, so thanks for inviting me. Um, and I will start by talking without the presentation, and it will come up a bit in a few slides. So I don't know about the audience really, but I assume it's a mixed audience. But you probably have a quite big interest in local first and offline app development. So my name is David. I live in Stockholm in Sweden. I have 2 kids and a wife. I'm educated in Stockholm University in mathematics and computer science. And I've been actually coding a lot even since I was a kid, and I've been also doing some music. Actually, in 1986, I bought my first Commodore 64, and that's where I got hooked into coding. So that's about me. And I don't know if everyone knows about IndexedDB. I suppose you do, but I don't know if everyone knows. So I'm briefly bringing up what actually is IndexedDB to begin with. And it's a database for all the web environments like browsers, workers, Electron and Capacitor, etc. That can run almost everywhere. And it's an object database with primary keys and indexes and ACID transactions. It's very similar actually to a relational database. It's sometimes misunderstood as a document database or something more fuzzy, but it's very strict with the ACID capabilities that also goes into SQL databases and so on. It's also optimized in that way. IndexedDB is not. I mean, you can have structured content objects with properties of arrays of objects, etc., and have a really deep structure like MongoDB, but it wouldn't perform well there in that sense. So it's more designed, optimized for as a relational database. It's actually backed by SQLite in all browsers except Chrome. So it could explain it. And it doesn't just store objects, JSON objects, it can store blobs, dates, binary data, etc. And also crypto keys and things like that, exotic objects. So it's quite cool, and it has a loose schema. You only have to specify the indexes and the primary key. So let me bring up my presentation. Frame rate 30, right? Okay. So what is DEXY then? I was talking about IndexedDB, and DEXY is a library that makes it a bit more fun and ergonomic to work with IndexedDB in the browsers.
We're currently just seeing the Discord.
Uh-huh. Good, do you say? Uh, let's see. I'm sharing my.
DBs.
Exactly. Yeah. Now you see the wrong window, but if I do this, what do you see?
Still the Discord.
Sharing the screen. Change, choose what to share. Aha, DLRF. Okay, sorry. Okay, now then, what do you see now?
Still Discord.
And Discord again.
Yeah, I'm trying to, but see, share a window up, make selection, go to this one. Yes. Now then, what about this? Oh, good. Okay, so Dexy, why would we need a wrapper for IndexedDB? Well, I mean, it's very nice. You have the a browser API that is standardized across all web-based environments, but it's a bit cumbersome to work with. So, and it has a lot of bugs to you need to work around. And so it could be good to have a wrapper. It's actually not possible. If you don't have a wrapper, you have to write your own wrapper. So I mean, it's just not possible to work directly against that API. Um, and Dexy also adds a layer of like a stack that you can plug into that can do things like sync, encryption, and other things. And what also Dexy adds is reactivity, which is not supported natively in the browsers, in the API. So you can, instead of just doing a query and getting the result, you can also subscribe to whenever this query would give another result, you will get a notification and you can re-render your app and so. So I think that's the most reasons to use Dexy or some kind of wrapper. And I think Dexy is quite unique with the reactivity part, but it could be others also that I'm not aware of. So yeah, here's some of the things I already said. And it's quite easy to do. You declare. It's like very straightforward. You declare the database, its tables, and its primary key and indexes to the left here, and that's typically put in some kind of module that you import, the DB module, and then in your application you can do a query where you query some friends here, old friends, or you could mutate the data using the DB instance. So it's a singleton instance in your application that you work with. The live queries are, these are two examples, one for React and one for Svelte. And the React one is actually doing a similar query as we did. This was the middle-aged friends. The difference is that we surround this, we encapsulate it in a use live query hook. So everything, this callback is returning a promise. And whenever something changes, like if you add a friend, remove a friend, or update an age of the friend or any other property, this will, these friends will be emitted, and you will, this component will re-render actually. And similar example for Svelte. You don't need a hook there because this built-in live query, which is not React specific, actually returns an observable compatible with the RX observables and the ECMAScript proposal for observables. And Svelte happens to be compliant with that, so you get actually a store here. So you can do a little loop here, and it will update as soon as you some other components, add a new friend or do whatever you want to do. So you get like the state management for free. Okay, so I'm just a brief summary of why I did this. I needed a desktop application back in 2011. I wanted to do it in 100% JavaScript to encapsulate with some kind of Windows application with a web area. This was long before Electron. So I had to do that, and I used local storage. I used some custom sync solution. But when I in the Explorer started supporting IndexedDB, I thought this is much better, much data to store, and much more possibilities to store objects. So I looked at some existing wrappers, but I'm that kind of guy that want to do things myself. I don't know if it's good or bad, but so I actually just thought I want to do this and have some. It must be simple. It must be more simple than simple and straightforward. So I call it straightforward DB. but it was a too long name, so Dexy was like shorter. And it's like a part of IndexedDB, made up to a name. But I open sourced it, but nothing happened. You never get detected just by open sourcing something. Maybe I thought that would happen. So what did I do to make it a bit more known? I actually sent an email to someone called Jonas Sicking, which was part of the WDC group. He was one of four that designed the IndexedDB standard. And he was from Sweden, so I thought I play the local card and email him about my new wrapper. And he advised me to write an article in Mozilla Hacks. The article was picked up by some people at Financial Time Labs that really loved it. And I was invited a year later to the Edge conference in London, together with Microsoft and Mozilla and Google in a panel to answer questions about the browser and the future. So that was quite an adventure for me. And that's also when I think it started off being a bit more known to people. But then the years went by. I was like coding, maintaining bug fixing, coding for customers. I got my daughter. Things were just moving on. But for some years ago, I added the live query support, the reactivity part, and I think at the same point in time, it's also when I started Dexy Cloud Beta. The big names chose to use Dexy, like WhatsApp, Facebook Messenger, ChatGPT, GitHub Desktop, Microsoft To Do, and some other like Loom and FlightReady 24. And it got a bit more popular. And a lot of repos are dependent on it. So where am I now? We are become a team. Benny is in the audience, I think, and Jesper and me, and our goal now is to make this a company that, with the help of Dexy Cloud, make the development of Dexy go forward with a faster pace, and it's really fun to work with. One new thing also I want to mention here is the YJS support that's been a huge focus the last year. I don't know if you have heard about YJS. I suppose many of you have. It's a competitor to Automerge, if I understand it correctly. And it's a CRDT library that is really focuses on optimizing the CRDT. And it has wide support in TipTap editor and other tools. So we added like a native support in Dexy for it. Right now, I'm in the process of extracting that code actually to a plugin to an add-on to Dexy, because it was a bit too much code, too heavy for the core library. But the purpose is the same, that you can in a property on an object that you store in IndexedDB, it could be a Y document, a CRDT document, and you can pass it to anything, any library in the ecosystem, like TipTap or anything, and it will work with it as an Y document, and in the background it will act as it was just a property of the object. And so it's still in beta right now, but it's been beta for a while, and it's going to be released quite soon. It's really cool things there. Dexy Cloud, it's the same idea here. I mean, sync can be really complex, and you probably know. And my idea here is to make a sync solution that is as easy as starting a Dexy app, declaring the database, doing some queries, and then just you have a URL to your database and you configure it, and that's it, and you're up and running. Of course, the sync, there are much more things that can happen in sync. You can have multi-users sharing between users. You need authentication and everything like that. But we pack it like you don't have to do anything of that. We serve you with a simple authentication solution, and And the sharing and access control is actually you maintain it totally offline the same way as you do with other offline data. And then you can replace the authentication, the custom authentication. Yeah, and it's also adjusted to work well with YJS documents with auto merging and zero conflicts. The YJ support, we're still in beta. If you want to try it, you need to have the next libraries, DexiNext, Dexi Cloud add-on Dex if you want to use it there. It's also possible without Dexi Cloud. If you use React, you need to have the next version of Dexi React hooks. We have a demo application and where you can start off trying it out. And I wanted to present something here. We had a hackathon this spring and we had a winner, and he was using YJ support, Dexi Cloud, and made a drawing application. So let's see here if the demo ghost is coming to us this time or not. Let's have two windows so you can see something. If I start a new drawing here, write something, and I go in here. Let's see. Is it this one? Yeah. You can see my cursor.
Yep.
It's the awareness of the
A second push.
YJS that is propagated via Dexi Cloud. And when I'm writing, I will also see it in real time. Of course, if I turn offline here, can I emulate offline? The network.
David, do you have two
Offline.
screens up? Because we can only see one of them.
Aha, sorry. That's pity because yeah, okay. I'm sharing. Well, I can explain what I'm sharing. I'm sharing two browser windows, different Chrome profiles, and I'm drawing with this one, and at the same time we're seeing the cursor and the drawing happening like momentarily after on the other one. So yeah, that was the YJ support with in this hackathon winner that is using all these features indexing. I think my
That's awesome.
time is over.
Yeah, if you stop sharing, maybe you can have it prepped for the Q&A section, or share the link into the chat, and people can kind of start posting where they're from. If I can have you, yeah, there we go. So next up, we have Carl. If you guys don't know about Mixpanel or Single Store, these are some of the more impactful things that are popping up and doing a lot of damage. And since then, he has started working on SQL Sync and Graft. I caught your talk, I think, I don't know if it was Syntax or like D-Log. It's one of the YouTube interviews that you did. And it reminded me a lot of like what Matt started working on before he moved on to Zero with CR SQLite. And he's also a fan, which is like, all right, wonderful. Let me get Carl in and have him do a talk. So over to you, Carl. I'm excited for what you'll share with us today.
Awesome. Thank you, Jans. Let me go ahead and share. If I did that correctly, you should see my presentation and hopefully no
Coming in
other
great.
like extra stuff.
Just the presentation. Yep. Wonderful.
Fantastic. Cool. Well, nice to see everyone this morning. It's like 8:30 for me. I don't know where everyone is around the world, but hopefully it's good time for everyone. Today I wanted just to share sort of something that I just really love. Like I love replication. I find replication super interesting. We use it in so much technology, and I think personally I like to think of replication as a way of modeling a lot more than what we might traditionally restrict to the world of replication. we usually would think replication is very in the like world of databases or like the world of like local first sync engines. But at the end of the day, replication is essentially copying something from one place to another. And we care about the same set of problems, whether that is a database replication stream or something like a REST API call. Sort of, we still care about both sides seeing the same thing, maybe sending small deltas and so on. So today I want to talk about replication and break down the difference between logical and physical replication, which I'm sure you've all heard about at some point. And we're going to sort of talk about the difference between those two types of replication, and then I'm also going to sort of talk about what Graft does differently. So as Jan's introduced, like I'm Carl, and I spent the last like 13 or 14 years in the database industry. Most notably, I worked on Single Store for 10 years. Single Store is a distributed relational scale out, OLTP OLAP database. It's sort of a hybrid system, and there I learned everything I could ever want to know about replication. So, without getting without any more preamble, like let's talk about replication. Also, Matrix, fantastic movie from my childhood. Just yeah, everyone, if you haven't seen it, go watch it. I'm sure everyone's seen it, but you never know. Cool. So let's build the like most naive replication system ever, like the simplest thing you could do. If your goal is to replicate state from one location to another location over time, the simplest thing to do is simply send all of the state every single time it changes. So we start here on the left with our initial snapshot. So this is the first version of our state. And as time continues to the right, we see that each time we make a change, like we change the color of these squares, and I hope these colors are coming across Discord, but you get the idea. These squares are changing color. Each time we change the color of a square, we send 100% of the data. Like the nice thing about this model, like I mean, obviously there's a whole bunch of bad things. Like for example, that's a lot of data we're sending. But the nice thing about this model is it's very easy to reason about, right? Like we can guarantee that both sides of the system are seeing the same data if we just literally copy all the data bit for bit. Sort of a nice model. It's a good place to start. However, as many of you've probably surmised, there's no way we would ship this in prod for large scale data. It just wouldn't make any sense. And so every replication system on the planet, whether that is like a local first sync engine using CRDTs, whether that is a database engine using like a write ahead log and snapshots, is essentially modeling replication as a snapshot and some kind of delta. So we can think of the snapshot as being the agreed upon initial state. In some cases, that could just be the empty state, right? Like if it's a CRDT that is completely convergent, our initial snapshot might just be empty. But in like a database, for example, we start with like a known state of the database that has a checkpoint of all the data at a particular version. And then over time, we apply changes. And instead of sending all the state, we literally just send the change. So in this case, I'm encoding the change as essentially the colored square and the number of the square we're changing, right? So this says we're changing the first square to green and then the second square to blue and third square to yellow and so on. And when we apply all these changes over time, at any point we can essentially materialize a like the latest state at that point, right? So we can think of this as being like a versioned log where each of these different changes represents a version, and over time we can sort of accumulate these versions into a new state. So this is basically how all replication works. This is a nice like mental model of it. But let's get into some of the more details, like what makes replication interesting, and most importantly, why do we have this dichotomy or like this difference between the concept of logical and physical replication? Like, what does that even mean, so to speak? So I came up with a Mona Lisa themed metaphor that I find like the easiest way for me to grok the like fundamental difference between these two sort of paradigms of replication. So here we go. We're going to draw mustaches on the Mona Lisa. So we start with a snapshot, which is the Mona Lisa in a completely untouched form. And in logical replication, we describe changes as something in the domain of the sort of set of possible changes that we can apply. So we essentially, in this case, this application might be like a drawing application, like Excalidraw or TLDraw. And if we're doing logical replication, we describe changes in a like very high level abstract way. We describe changes as like, for example, here we have like a draw operation, and we say, here's the position we're going to draw, and here's the thing we want to draw in that position. And the important thing to note here is that this is very coupled. Like the replication engine is essentially transmitting these objects, and these objects are very coupled to the application domain, like the sort of business logic of the application, right? So if the application has no idea what a draw is, it has no way of applying this change to the model, right? It needs to know how to interpret the changes. And this is fundamentally the logical aspect of logical replication, is this interpretation of domain-specific state or domain-specific deltas. So when we apply this change, of course, we get the beautiful Mona Lisa with an amazing mustache on it, and we've accomplished logical application. Now, obviously we're, in real world, we're not doing like one image, we'll do like 100,000 images, and we're not doing like, adding mustaches, we're doing like arbitrary image operations. But this is the fundamental aspect of what makes something logical as opposed to physical. So if that's logical, what is physical? So we'll do the exact same operation, but we're going to do it using physical replication. And in physical replication, the replication engine actually has no idea of the set of operations that can happen. The physical replication engine only has the ability of transmitting bytes and guaranteeing that they get transmitted wholly and correctly and placed in the right location in the destination. And so we can think of physical replication as doing the same operation, except we're only sending essentially a patch. We're saying, here's some bytes that we want you to put in the destination, and here's the exact value of those bytes. And the important thing to note here is that unlike in the last slide, like I'll switch back, and unlike here, we only have to send, of course, the mustache because we're doing an actual like operation on the data to compute the state. Here, we're actually sending the full-blown patch of bytes, like all the bytes that are going to be literally copy and pasted directly into the image. So the way I like to think of physical and logical is that physical operates in the domain of bits and bytes, the actual like raw physical data structures that are ultimately going to be written to disk and stored in sort of storage systems and operated on directly by database engines. Whereas logical application operates in sort of a higher level like abstract domain of objects and operations, which can then be interpreted by different engines and applied to data. So I hope that sort of gives a good intuitive understanding of the difference. I also created a nice little table of sort of the key aspects of logical and physical, and some of the trade-offs that you have to take into account. So just to go through this table really quickly, we already talked about the granularity, right? So the physical is in the page world or the bytes world. Logical is more in the like operations world or domain world. Portability is the sort of notice that logical operations, because they're in this like abstract world, you could use logical replication to move between fundamentally different execution engines. So for example, if you're replicating a database workload, let's say you're replicating from MySQL to Postgres, you could use logical replication because the actual like way that the operations are represented in the logical replication stream is very abstract to the underlying database. It may use some like custom types here and there, but fundamentally it's a high enough level abstraction that you can convert those abstractions to Postgres sort of abstractions. So you can sort of map the data across, which makes logical replication extremely portable and really easy to work with. Whereas in physical replication, because we're operating at the like world of bytes and bits and the lowest sort of level of the storage engine, we have to replicate to compatible storage engines. So if you go from MySQL to Postgres and you send the raw data that they're storing on disk, it's not going to work very well because Postgres has no way of interpreting it, doesn't know how to interpret the way in which MySQL writes data to disk. So we can sort of think of portability as a big trade-off, which often makes logical replication a lot easier to use in especially like very disparate workloads where you have many different systems operating on the same data. But with any advantage, we often have a cost, and that cost is performance. Logical replication has so many more things that have to happen from one side to the other to be able to encode data into a logical replication stream. So we have to basically keep around those logical changes to be able to send them to downstream consumers. And then when we receive them on the consumer side, we have to actually apply them. We have to basically verify that these changes can be applied. We have to sort of do operations on the data structures. If we want to support undos, we have to actually support keeping around like prior versions and being able to like reverse the operations that are being applied sometimes, depending on how you store your data. So all of these things can add up to a performance cost that sometimes is not reasonable. And that happens, that shows up very often in database world. So if you set up a high performance Postgres replica, so you take like a Postgres instance, create another Postgres instance, and you say replicate to each other and do it really, really fast, the fastest way to do that is use physical replication, because at the end of the day, physical replication is just going to send bits and bytes over to the destination. There are some checksums that can run, which are very, very fast. But one of the most important aspects of physical replication is that when we're done, when we've applied all the changes, we can actually just checksum the entire database, and we can verify that we see the same result as the sender. And that's much, much harder to do in logical replication, especially when storage engines are different. And so even things like verifying that two nodes see the same thing is much, much cheaper and faster in physical world. The third big one is data agnosticism. And so the idea of data agnosticism is that we like the actual data that we encode in the replication stream itself is agnostic to the domain of the data. So in logical replication, as we showed before, we have to actually teach the replication engine that we're sending these like objects, these things that represent like draw calls, for example. And so the data in the stream is very coupled to the like application itself. It has to know about, maybe it has to know about the schema, for example. And this can sometimes lead to complexities and problems in, for example, schema change scenario. So where you have a relational database, you change the schema, you alter the table, you add a column, you do whatever. Sometimes that can cause difficulties in the change stream because we have to sort of find a way to encode that. Whereas in physical world actually doesn't care. It doesn't actually care whether or not you're changing a single row, you're updating a cell in a row, or you are changing like the schema of an entire table. Because at the end of the day, it's representing those changes as essentially just physical changes on disk, like some set of bits and bytes are changing. So it often can be much easier to have physical replication be a little bit more robust towards arbitrary changes. We don't have to change the sync engine to be able to add a new kind of change. The last delta, or the last sort of trade-off, is this interesting thing that I'm super interested in, which is partial. And one of the reasons why logical replication has shown up so much in the world of local first, especially with like the advent of CRDTs, conflict-free replicated data types, is that it can be made partial really easily. And what do I mean by partial? What I mean by partial is that if you have some like leader node with like a bunch of data, and you want to replicate that to multiple follower nodes, but each of those followers you want to send a different partial subset of the data. Logical replication, you can do that by just literally filtering the operations that you send off to the individual nodes. Because they're these high level operations, they're much easier to work with. Whereas in physical replication, it's really hard to filter arbitrary changes to essentially bits and bytes on disk. Like, how do you differentiate between like a schema change operation versus like a row change operation? And also you might have to take into account like different versions of the execution engine. Because you're sending data at this very, very like low level representation, it can sometimes be really difficult to do some kind of like partial filtering of those data structure transmissions. So all of this is to say, this is how I like to think of the sort of set of trade-offs between logical and physical. There's a lot of nuance here, so don't take this as like gospel. There's a lot of logical engines that do physical things, and there's a lot of physical engines that do logical things, and so it's not like a perfect set of trade-offs. But this is generally the sort of way to think about these two sides of the coin. At the bottom here, I just added some example places where we tend to see logical versus physical replication showing up. But let's move on to what I'm really excited to talk about, which is Graft. So the last like 2 years, I've been working on this project called Graft. And I've gone in a lot of different directions. It hasn't all been working on Graft. I've worked on a project called SQL Sync, which was my experimental multiplayer SQLite that did not use CRDTs, which is very like it's similar in usability but different in implementation to something like CR SQLite by Matt, for example. So it was just a different sort of approach. And then I pivoted to realizing that what I really wanted was a physical replication engine that had the benefits of physical replication. So it had the speed of physical replication, it had the data agnosticism, the simplicity of physical replication, but it could do partial replication. That was like the fundamental question was, what does a like a partial physical replication system look like? And so I spent a while trying different things. I wrote a couple different implementations of Raft at this point that have different approaches. And I ultimately ended up with a very simple idea, which is what if we just take regular physical replication and we change exactly one thing about it, which is that instead of sending the patch, like the description of where the change is, along with the actual data that changed. Instead of doing that, what if we just send the description of what changed? So if you think about that for a moment, what we've done is we've dramatically decreased the cost of the actual replication stream that's going out to the clients, because now we're sending very tiny descriptions of potentially very large changes. So to make this more concrete, if we are sending like rows from one database to another in physical replication, in normal physical replication, we would send all of those rows to that replica as they change. So the actual like bits and bytes of the change. However, in Graft, we would only tell the replica which rows change without actually telling them essentially the actual changes. Now, you might be wondering, why is this useful? Now we just have less information. So this is sort of what it looks like from the leader and replica perspective, right? So we start from the same snapshot, just like normal, and then we basically send over a patch. And now the replica is like, cool, well, I know there's a change. Like I know that there's something in this location in the middle of Mona Lisa's face, but I have no idea what it is. Now, why is this an awesome thing? Well, let's say that this is like a local first workload. This is some device workload. And this device happens to only be rendering Mona Lisa's hands. Then this device has no reason to actually receive this data. It's happy that it knows that it changed, but it doesn't actually want to get that data proactively. Because we basically, if we proactively send all the data, we have to send all of the data constantly to clients. However, later on, this app, maybe the user is doing like an image viewing app. They're looking at Mona Lisa's hands and then they scroll up and they look at Mona Lisa's face. We want to quickly be able to get, oh crap, we have to go get that thing. We have to go figure out what changed. And so Graph provides a protocol to be able to do this request to say, hey, I, like at a later point, I lazily want to go and download that patch that we missed earlier. And the important thing here is consistency. Graft, this protocol obviously looks very, very simple, but the important thing here is that when we send that request later, we want to basically make sure that we see the exact patch that we missed and not some other patch that may be changed in the middle. We want to basically guarantee that the client sees fully consistent images. They don't see torn images from two different sort of sets of changes. And that's what makes Graft a little bit tricky. But once you figure this protocol out, it allows you to essentially decouple the idea of change detection from change propagation. And that leads to a system that provides the benefits of physical replication, like the performance, the simplicity, the ability to do consistency checks really easily, the ability to map arbitrary data structures to Graph without Graph knowing about the data structures, like for example, SQLite or maybe other database engines or like a Fuse file system. We get all those benefits of physical replication, but now we can run those physical replication workloads on small devices that we could never put all the data on in the first place. So that's the fundamental idea of Graft. And here's sort of like the trade-off page. As I said, Graft basically gets that partial. Graft loses a little bit of performance because we now have this additional round trip, which we can make up with by doing amortization. So we could basically, even though we're a little bit slower because we have to do extra round trips, we only need to request the things we actually care about. So if you think about like the amount of bandwidth that we end up using a lot less because we don't need to download all the data. We also don't need to see all the versions of all of the different bits of data. We can skip forward really easily to like later versions. And Graft also is just designed to be running in like fairly embedded systems, so it's very optimized for performance. So it's very very fast compared to like Logical, for example, for like the same workload, but it has those advantages of physical, and it ultimately leads you to be able to run physical replication workloads on edge and device environments, which is my whole goal. That is all the time. I just wanted to keep this really tight, really clean. I'm very happy to answer questions, but thank you so much. If you want to learn more about Graft, I have the QR code on the left, or just go to graft.rs. And if you want to start us on GitHub or me on GitHub, it would be really appreciated. And thank you so much.
That was a wonderful talk, Carl. And and it needed being walked through the sort of physical and logical kind of gaps. There's a similar sort of CRDT world where state-based transforms and operation-based transforms to avoid conflicts. And this was a nice addition to some of the talks that we've had, sort of orthogonal to this. If you don't
Awesome.
mind, stop sharing, and then I can pull up Jay's bio. Yeah, for folks doing conflict replicated things, I'm sure you've already known about that. And reactivity on stores like LifeStore have these operation transform models, write ahead logs, all of these things, they're sort of in the same zip code, but have never really been laid out so succinctly in the previous talks. Uh, Next up, we have Jay, such a big fan. Caught up in Berlin for the local Sync London. Sorry, we caught up in London for the Sync London event, and the recordings will drop pretty soon. He's been working on Legend app. It's a wonderful note-taking platform, I want to say. It's hard to call it an app. Composable between your calendar, tasks, and notes. It's hard to describe, so you just have to try it. And he's worked on at EA and one at Microsoft on Windows and Surface, and sort of reactivity was sort of how he kind of makes a living. But I won't say more than that because it will be really interesting to hear about it. Personally, React Native lists have been the bane of my existence, and I think it's finally solved with Jay's platform. Over to you, Jay.
All right. So let's share. All right. Sharing looking good.
Yep, you're coming in great.
All right. I think we wanted to just change the settings on that. Yeah.
It's coming in
Okay.
good. So
All right. So I want to talk to you about um, doing local first apps with any backend and extremely high performance. So I built this state library called Legend State, which powers all that. So first, a little bit about me. I make Legend, which is a local first productivity app, which combines documents, calendars, and a built-in web browser. Some of my users have millions of items that need to be filtered and sorted as they type. So performance and sync are really critical. And I'm also working on Bravely, which is a platform for mental health therapists to run their practice and collaborate with their clients. Healthcare data has really intense security and privacy requirements. Plus, it needs to work reliably in poor network conditions. So we do not want to ever lose any data. So doing local first well is essential for us. So when you're building a local first app, that usually means you're managing three different things. You have your local app state, you have the data on the server, and then you have potentially a sync engine that's built on top of that. Sometimes that sync engine is a whole other server in itself. Sometimes it's just some client-side logic. But in Legend State, the state handles the sync for you. So you just have state that syncs itself. So let's talk about how that works. So, sorry, the core primitive is the observable. Uh, Other systems call this concept signals with hierarchy or deep signals. It's not really clear what it should be called. But yeah, you can create observables from any structure. They can be objects, arrays, or primitives, strings, whatever. And we use a dollar suffix on variable names just as a convention to indicate it's an observable. Um, So the API is pretty simple. You just get to read, set to write. There's no weird immutability. There's no actions or reducers or any of that. It's just direct manipulation. And it works for any level of nesting. You can set at the root. You can set way deep down in a hierarchy. Everything works fine. So as you dot through an object, it creates a proxy for each child dynamically. And that doesn't modify the data at all. It's just a proxy wrapper that adds functions to enable the change tracking. So in React, we have a useSelector hook, which tracks the observable, and it automatically re-renders when it changes. So this is a key difference from useState or other state libraries, because each useSelector call tracks only the specific data that it accesses. So in this example, when email changes, this component's only using name and not email, so it won't re-render. It only re-renders when the name changes. So this granular tracking is really good for performance. But even better for performance is to just not render at all. So we can use this memo component, which makes a tiny little element that re-renders itself when the name changes. And then we have this input component, which we can two-way bind to the observable. And so this outer profile component actually never re-renders while you're typing. So this is what that looks like in practice, with a little flashing box every time an element renders. In normal React, you have to lift state up all the way to the top. And so every time something changes, it has to pass all the way down, rendering everything in between. But in the observable version, it re-renders only the tiniest elements that actually change. So this, along with a lot of optimizations, is how Legend State is significantly faster than other React state libraries and even vanilla React. But this isn't the performance first meetup, so we'll focus on the sync part of this. So because an observable is a proxy that doesn't touch the raw data, we could actually have it point to anything. So a child of the observable could just be a child in an object, but it can also be a function, which lazily computes a value when it's accessed. So we can make a computed observable child with just a function. If you call .get on it, it treats it as an observable. Or we could use it to make a totally new object. So we have this feature called a lookup table, where if you use it as an object with a key, it just points into a different observable. So then you're two-way bound directly into another observable. And this works well because the computeds are lazy. So it creates a new proxy dynamically as you access them. And that laziness allows something really interesting, which is that an observable could point to a promise. So since it's lazy, it doesn't do anything until you get it. And so when you get it, it triggers the fetch, and it immediately returns undefined because it doesn't have anything yet. But then when the fetch resolves, it updates itself in place. So then if we use that observable in a component, it'll initially render with nothing. And then as soon as the fetch is completed, it'll just rerun itself with all the data that came in. But fetching is more complicated than this. So we have a little plugin where all you need to do is just give it a URL, and it'll manage a bunch of the complexity for you. Interestingly, this plugin can also track all the changes you're making, and so we can send them back to the server and do a two-way sync. So now we have this messages observable, which is two-way bound to your server. And so when you modify it locally, it just syncs it. So that's where it gets really interesting for local first apps, because Legend State doesn't just know that something changed. It knows exactly what changed, where, and how, because every change includes the path in the object, the new value, and the previous value. So we can understand the user's intent because we know exactly what fields are changing. So this granular change tracking is what makes Legend State perfect for a sync engine, because we can use this change as metadata to determine what to sync. So with all that information, we can build this simple sync engine. So we have a little synced helper, which connects an observable into a sync engine. So we can just get the profile from the server, and then when we modify it, we set it back to the server. And we can also persist it to local storage, so that when it loads, it already has the cache data from local storage. Or we could use IndexedDB, but then that becomes asynchronous, and that's a whole other thing. So one way to make a sync engine could be to send the changes array to the server, and then let your server figure out how to apply those changes. Or we have a synced CRUD plugin for CRUD backends to make that stuff easy. So you just need to give it your CRUD functions. So the plugin figures out which rows were created, updated, or deleted, and produces a minimum delta to send to the server. So if you update the text of a message, it just sends a partial update with only the changed text. With a few more options, we have a whole local first sync engine. So it caches all the changes as you make them, and it retries them until they succeed. So this lets you use your app fully offline and know that once you come online, everything will eventually sync. And using the updated at timestamps in your data, we can query the server for only things that changed after that. So then combining that with the local cache, we can basically start your app with everything already there and then query for just give me everything that's changed since then. So this is a big bandwidth and processing time saver. So the key to making the retrying work is because we know which fields are changing, we can cache those pending changes. So we can save where in the hierarchy you change something from what and to what. And then we can just hold on to that until those saves go through successfully. So when we restart the app and we come back online, we first receive the remote data, then we rebase these changes that we have cached on top of that. If anything is still different than what the server has, we try to send it again. So in Legend State, you can actually mix synced and local only state in just a giant store if you want, or you can use lots of different discrete observables. It's kind of up to you. They are lazy, so they only sync when you access them. So you can set up a massive store for everything. So in my app, Bravely, we have like a 2,000 line file that has everything that could ever possibly sync in it. And then different pages use different pieces, and it triggers the sync as you access them. Or your app might prefer to just sync everything all at once, and you can do that too. So since all of your data is in observables, you also get all their nice properties like easily computed values. So when the synced data updates, it automatically triggers the computed to update. And so then your components can just read the computed values, and they will update themselves as the server data changes. And if you want to display loading states, we have every kind of metadata you need to display all of that. So to do local first really well, you probably want to have real-time updates. So we have this subscribe function that's on the sync plugins. So you can set up your own subscription. So for example, I have just a SQL database, and then I use Firebase as a real-time thing where I just basically post timestamps to Firebase, which tells me that the data changed, and I can just run my SQL query again using the updated at timestamp, which is very convenient. So because the sync engine is in the state, it doesn't actually care what the backend looks like. So I think this is one of the things that make it cool is it can work with any backend. So we currently have plugins for Supabase, Firebase, Keel, React Query. Looking at making one for Convex soon. You can build your own plugin on top of this pretty easily. It doesn't even need to be a server. It's just a promise. So you could two-way bind your state to anything like calling functions across the Electron bridge or using device APIs. So in this example, you can bind directly to the brightness of your phone or something. So since the sync system lives in the state, your front-end code doesn't need to know anything about it. It just gets and sets observables. So you can prototype your UI just with local state, and then you can add persistence to that to start caching it. And then you could hook that up to Supabase to start quickly syncing it. And then you could change your whole backend provider and just swap the sync plugin. And your app code doesn't care. It never has to change. So you never have to change your components or anything. I've actually done this before. I swapped from Firebase onto a SQL-based system, and I never had to change any components. I just changed the state system. This works on React and React Native. It could potentially work in any other front-end framework too. My experience is in React, so this is where I live right now. So wrapping up, I think Legend State is interesting because it gives you the best possible performance in React, and it's also a very powerful backend agnostic sync engine with, I think, simple developer experience. So I hope you'll give Legend State a try, whether it's for your local first sync engine or just to make your apps really fast.
God damn, Jay. Like it was like casually dropping bomb after bomb on that talk. This was like the primitive. Uh, I personally definitely needed this thing, and then like, so we were already kind of adopting Legend State. The observable pattern we were building out locally and running a pilot with Live Store. We're not very jazzed on being pinned to a database just to do an OT-based sort of like optimistic update solution. And the
Yeah.
primitive where you just like dropped in a fetch as part of the key access was just like, what? That was what we needed. Uh, just so I don't keep being all complete fanboy on you, let's kick off the questions part of this meetup. What we usually do is we stop the recording and